All right, today we're going to do something a little different. We're taking a deep dive into natural language processing, but we're going to look at it from an engineer's point of view. We're not just going to cover the what, we're going to deconstruct it piece by piece, almost like we're designing the whole system from scratch. So let's just jump right in and frame the core engineering challenge.
For us, this is instantaneous. Our brains use context, and the meaning of the word bat is just obvious. But for a computer, it just sees a sequence of characters, B, A, T. It has zero context. So teaching a machine how to untangle this kind of ambiguity, well, that's really the fundamental puzzle of NLP.
So, where does NLP actually fit into the huge world of technology? The best way to think about it is as the specific branch of artificial intelligence that is totally obsessed with language.
At its heart, NLP is the bridge between how we communicate and how machines execute commands. The goal isn't just to, parse words. It's to truly understand intent, to manipulate the information behind the words, and, this is crucial, to generate coherent human-like language in response.
This chart really says it all. NLP isn't some island. It's the critical intersection of these massive fields. You've got the raw material, which is human language. You need the algorithms and the hardware, which come from computer science. And you need the overarching goal of building intelligent systems, which is what AI is all about. NLP literally cannot exist without drawing from all three.
Yeah, NLP is a true synthesis. It's using the nuts and bolts, the algorithms from computer science, and it's powered by these incredible learning engines for machine learning, all sitting on top of the mathematical backbone of statistics. But, and this is a big but, it's all guided by the deep domain expertise of computational linguistics to make sure the models actually make logical sense and respect the structure of language.
Okay, so let's shift gears a bit. It's time to put on our systems engineering hats. For this next part, we're going to stop treating language like it's some kind of magic and start treating it like what it is, a really complex system, but one with fundamental, parsable components.
This is the first question any engineer has to ask, right? Before you build a machine, you have to intimately understand the raw materials you're feeding it. And in our case, that raw material is language itself. So what is it made of? We can think of language as this pyramid, built from the ground up. We start at the very bottom with the basic units of sound, the phonemes. Then we combine those into units of meaning, arrange those with syntax, and finally, right at the top, we interpret the whole thing with context.
Think of phonemes as the atoms of spoken language. Little sounds like k, a, and t. On their own, they're meaningless, but put them together and you get cat. For an application like Siri or Alexa, the very first engineering hurdle is just distinguishing these tiny sounds from each other in a noisy audio signal.
Okay, moving up a level, we find morphemes. These are the smallest chunks that actually have meaning. Take the word unbreakable. To us, it's one word. But to a machine, it's actually three distinct units of meaning. Un, which means not, break, the action, and able, which means can be done. Understanding this is totally key to understanding how words are formed.
Now, closely related to morphemes are lexemes. A lexeme is basically the concept that groups all variations of a word, like run, runs, and running, into a single base form. This kind of analysis is absolutely foundational for core NLP tasks like tokenization and a process called stemming, which is all about getting words down to their root form.
So, we've got our meaningful units. What's next? Well, syntax is the blueprint for how to assemble them correctly. It's the grammar of a language. And in NLP, we often visualize this as something called a parse tree, which is really just an engineer's diagram of a sentence's structure. It shows how every word relates to every other word.
Finally, we reach the top of the pyramid, context. This is the really tricky part. It's everything that isn't explicitly written down. It's common sense, it's world knowledge, it's the history of the conversation. Context is the ghost in the machine that lets us solve that bat ambiguity we started with.
And we can even break context down into two parts, semantics and pragmatics. Semantics is the literal dictionary meaning. Pragmatics is the implied meaning. So, if someone says, it's cold in here, the semantic meaning is a weather report. But the pragmatic meaning, what they really mean, is probably a request. Please close the window. Teaching a machine to tell the difference between what is said and what is meant, that's still a massive challenge in NLP.
Okay, so we've deconstructed language into its components. The next logical engineering question is, how do we actually build systems to process all this stuff? Well, historically, there have been three major approaches.
You can almost think of the history of applied NLP in 3 eras. First, you had the rule-based approach, where humans painstakingly wrote all the rules. Then came the machine learning approach, which could learn rules from data. And now we're in the modern deep learning era, which uses powerful neural networks to learn even more abstractly.
So the first approach was, well, to write all the rules by hand. Experts would use tools like regular expressions to codify their knowledge into the system. Like writing a specific pattern to find any email address in a block of text. This is super precise, and you can always explain why it did what it did, but it's also incredibly brittle. The moment it sees a new pattern it wasn't explicitly programmed for, the whole thing just breaks.
The next era was a total paradigm shift. Instead of giving the machine rules, we started giving it examples and letting it figure out the patterns on its own. The critical step here, though, was something called feature engineering. A human engineer still had to manually and very cleverly convert text into numerical features that the algorithm could understand. And honestly, the system was only ever as good as those handcrafted features.
And that brings us to today, to the deep learning approach. The absolute game changer here is that it automates feature engineering. Architectures like the now famous transformer can learn the best numerical representations directly from raw text. This is what unlocked state-of-the-art performance on so many tasks. But there's always a trade-off, right? These models are often complete black boxes, and they are incredibly data-hungry.
Okay, that's the theory. But what does an NLP project actually look like in practice? Let's walk through this standard engineering pipeline, all the way from getting the data to deploying a finished product. This 5-step pipeline is really the bread and butter of applied NLP. It's a fantastic roadmap for pretty much any project you can think of. First, you get the data. Then you clean it up. Then you turn it into numbers. Then you train your model. And finally, you push it out for users and keep an eye on it.
Step 1 is always data. Is it sitting nicely in a clean database for you? Great. Or do you have to go scrape it from the web? Is it trapped inside a mountain of PDFs? And hey, what if you just don't have enough? Well, then you turn to clever techniques like data augmentation to artificially expand your dataset.
Raw text from the real world is always a mess. So the next step is pre-processing. After you do the basic cleaning, fixing typos, removing emojis, you apply that linguistic analysis we talked about earlier. Part of speech tagging, that's syntactic analysis in practice. Lemmatization, that's the application of morphological analysis to find a word's true root form. It all comes back.
Feature engineering is the art of turning that cleaned text into numerical vectors. A machine learning model doesn't understand words like happy or sad. It understands vectors of numbers. This step, especially in a traditional machine learning project, is often the single most important factor in its success or failure. Now that we've got a feel for the build process, let's clarify a really key distinction in this field. Broadly speaking, NLP systems either read and understand language, or they write and generate it. Natural language understanding, or NLU, is all about machine reading comprehension. Its job is to take a messy, ambiguous human sentence and distill it down into a structured command that a computer can actually execute. It's about pulling out the core intent and the key entities from the noise.
And on the flip side, you have natural language generation, or NLG. This is the output side. It does the complete reverse. It takes structured data, like numbers in a spreadsheet or a weather forecast, and translates it into a human-readable story or a spoken response.
This table just makes the distinction perfectly clear. Think about a voice assistant. When you ask it, "What's the weather?" that's an NLU problem. It has to interpret your intent. When it gets the data and replies, "It's 72 degrees and sunny," that's an NLG problem. It has to generate a response. Simple as that. NLU is input, NLG is output. We've covered the components, the architectures, and the pipeline. So for our final section, let's look at the frontiers. What are the challenges that continue to stump even our most advanced models? And here we are, full circle, right back to ambiguity. Besides the lexical ambiguity of our bat example, there's also syntactic ambiguity. Think about this sentence. I saw a man on a hill with a telescope. Who has the telescope? Do I have it, or does the man on the hill have it? Resolving that requires world knowledge that models just don't have yet. Oh man, irony and sarcasm are exceptionally difficult. Why? Because the intended meaning is the complete opposite of the literal one. When someone says, "Oh great, another meeting," the sentiment is obviously negative, but the words are positive. Detecting this requires understanding nuance and tone, something models are notoriously terrible at. Language, especially online, evolves at a dizzying pace.
NLP models are often trained on static, formal text like Wikipedia, so they really struggle to keep up with the fast-paced, messy, and constantly changing nature of how people actually talk to each other. The language you find in legal contracts or in a doctor's notes, it's practically a different dialect. It's filled with jargon and a ton of assumed knowledge. A general-purpose model that was trained on web text is going to perform very poorly in these specialized domains unless you do a lot of specific fine-tuning.
This one is a really sobering challenge for the field. The vast majority of progress in NLP is in high-resource languages like English because we have these massive, clean data sets. But there are thousands of other languages that simply lack this data, and that's creating a pretty significant technological disparity across the globe.
And this brings us to our final thought. Today's models can generate text that is often completely indistinguishable from something a human wrote. But is generating statistically probable words the same thing as true understanding? As we continue to push the technical boundaries, maybe the biggest questions we have left aren't about algorithms or data, but about the very nature of meaning and intelligence itself.